In a previous slide, Pastel found out sodium ammonium tartrate salt has two different shape of crystals. Actually, two crystals, the shape of two crystals were in a mirror image. And later on, he found out these two crystals are in a mirror image relationship in the shape of crystals, also in the configuration of the molecules. And that's the first finding about the enantiomer or stereoisomers in the world. Actually, the sodium ammonium tartrate is the dicarboxylic acid, and there are several kind of dicarboxylic acids in a cell. We can frequently find the dicarboxylic acid, and though these are the dicarboxylic acid we always see in a biochemistry. Tartaric acid, and sodium ammonium tartrate is a salt of a tartaric acid. Malic acid, succinic acid, and fumaric acid, and malic acid. Try to remember the structure, right? Now, the most important thing in this chapter 5 is the sequence rule for the specification of a configuration. Sequence rule describes how you can distinguish enantiomers, okay? So, for example, let's say you have four groups around the carbon is different, and this is a chiral carbon. And 1, 2, 3, 4 represents the sequence priority of the atom or atomic groups. What is the sequence priority? Okay, the most important, the simple example of a sequence priority is an atomic number attached to the carbon. For example, if this 4 is hydrogen, then the atom attached to this carbon is hydrogen, then atomic number of hydrogen is 1. So we use the atomic number as a guideline as a guide for the sequence priority. If this number 1 is CH3, then the atom attached to the carbon is carbon. So in that case, 12 is the atomic number for 6 is the atomic number for the carbon. So 6 is higher than 1 of the hydrogen. So we can say number 1 is in a higher sequence priority than number 4. Right? So we can assign the sequence priority for each of these group or atoms. Let's assume the sequence priority, this is number 1, 2, 3, 4. Then in order to assign the configuration of this isomer or this mirror image molecules, you put the lowest sequence priority in the back, like this. Dotted line represents in the back, and wedge represents coming toward to you, okay? Dotted line is going away from you, behind of the paper. So once you put the lowest priority in the back, then you arrange the rest of 3 atom or atomic groups, and then look at the direction of a sequence of priority. In this case, 1, 2, 3. So it's a clockwise. If it is clockwise, then we assign this as a R. R is just like a right. Okay. So also when you draw the R, when you write the R is like this, and this is R. Okay. This is the mirror image of this compound. So it will have opposite configuration, right? So 4, 4, 3, 3, 2, 2, and 1, 1. Now you put this 4 priority in the back, and you look at the relative arrangement of these 3 groups, like this, then you immediately know that the direction is like this. If direction is like this, then we assign this as S configuration, because when you write S, you write like this, okay? And we can, and now, so the sequence is very simple, but there is a problem. There are a couple of problems. If you have the same atoms attached to the carbon, what happens? Then you go to the next atom. Okay, for example, if you have a carbon like this, now you have oxygen and you have oxygen, and then they are the same, then you go to the next one, all right, like this. Then so if the decision cannot be reached by the ranking of first atoms in the substituent, look at the second, third, and fourth, all right. Now rule number 3, this is the last one. If you have a multiple bond like this, you consider this as C attached to oxygen and oxygen attached to the C again. So C attached to the oxygen, and there are 2 oxygens, so you put these 2 oxygens. But this oxygen attached to the C 2 times, so you pick up one of this oxygen and then put one more carbon here. In this way, C has 2 oxygen bonds, oxygen has 2 carbon bonds. And when you consider the priority, you consider this first. And you go to the second. If you have a H and O, you go oxygen here, right? But this is also oxygen, but it is better to have the third one, because if it's the same in the oxygen, then you will have to go to the next one. Therefore, when you assign the sequence priority, this is the first atom, will be the second atom, will be the third atom. Okay. This is another explanation using just like Newman projection. You have your eye set. This is your eye, all right? And dotted line is in the back of the paper, and dotted wedge is in the back of the paper. Just wedge is coming front of the paper, and line is included in the paper. Okay. So if you put your eyes here, and the 4 is the last one, so you put it in the back, you draw the Newman projection. You cannot see the 4 because in the back here. Now 1 will be left side, 2 will be right side, 3 will be in the bottom. So in this case, this is R configuration. Okay. You can apply the same principle here. You immediately know this is S. Practice Saturn in your home. This is a real molecule, right? This is carbon, chiral carbon. If you look at the sequence priority, this will be 1 because oxygen, carbon, carbon, H, so 1. But these 2 carbon, this is the same carbon. In this case, next atom is the hydrogen. In this case, next atom is the oxygen. So this one is number 2, this is number 3, and this is number 4. So if you want to assign the configurations, you have to look at this molecule from this side, because this is the last one. You should put it in the back, and then if you draw the Newman projection, OH will be right side, CH3 will be left side, COH will be bottom side. So this should be this will be R form. Okay, this will be try to look at what this is. All right. Now when you draw a structure, there's a convention that the vertical line represents the groups sticking out. Okay, perpendicular line represents the substituent pointing away from you. Okay. Now I explained what the vertical line means and what the horizontal line means. All right. So we can draw the 3-dimensional structures and try to assign S or R. In most of cases, most of amino acid in the biomolecules is they are S form, and the carbohydrate is they are R forms. All right. But usually most of the textbook uses D or L instead of R or S configurations. D or L is based on optical activity, whether they rotate light clockwise, then that is D. If the light rotates anti-clockwise, then it's L isomers. Fortunately, there is a relationship between D, L, and R and S in amino acid and carbohydrate. Okay, and most of D isomer of the carbohydrate is L uh, uh, yeah, S. Most of L isomers is S configuration. Most of D isomers is R configuration. Okay. Okay. Uh, we learned about sequence rules of chiral compounds. There are many exercise problems in your textbook, so try to practice how to assign R and S for each compounds, right? Also work on the homework, and you will have chances to practice it. Thank you. See you next time.